Dave Binkley, I'm here to tell you a little bit about a replication we conducted. It's interesting. It's a replication of a negative result, right? So the replication falls under the category of conceptual in that we address the same problem, but we use very different methods. Right? I'll talk a little bit about that at the end of the talk. It's also a generalization and an extension. The generalization comes from our use of a different population of subject programs, while we extend the original work by extending their visual analysis of the data that they gathered to provide more statistical rigor in our results. Right? So the experiment we're replicating has a number of conclusions to it. We actually find a lot of the same things. The thing I want to focus on here, right, is the bit I've highlighted, and that is that the length of an information flow, right, is not indicative of its strength. So that not is the negative part of this, right? Let me explain this a little bit more detail in our terminology. We think about this in terms of squeeziness. We have a domain in the program and some code, and then that code kind of squeezes the domain. So you get sort of less information out by the time the code is executed. A classic example of this, which is a pretty dramatic squeeze, would be the assignment x gets x mod 2, right, which takes the original value of x, which might have quite a large number of values, and squeezes it down to just 2. Right? So our supposition is more code, more squeeze. Right? I realize you can construct short pieces of code with lots of squeeze and long pieces with none, right? But if you take a random piece of code off the shelf, you'd expect the longer it is, the more likely it is to sort of squeeze the domain a little bit. So we set out to measure this, right? We measure the length of the code using dependence edges or dependence paths and a dependence graph. We measure squeeze as the expense of generating test data. So let me tell you a little bit more about that. We measure the length in 3 different ways. We consider data dependence-only paths, control dependence-only paths, as well as paths intermixed, both control and data dependence. For the testability, we use Iguana, which targets predicates, so our analysis targets the predicates in the program as well. Iguana is trying to find test data to cause a given branch in the program to go either true or false, right? We use as our explanatory variable the number of evaluations it takes Iguana to find that test data. Right? Iguana actually implements 3 techniques: a random one, which provides a nice baseline for the complexity of the search space, right, as well as a genetic algorithm, and then an implementation of Curl's alternating variable method. In the analysis, we ended up with 416 predicates, right? We pulled 416 predicates, but I really only able to match about 282 of those. The paper goes into the details there. It's interesting to note that Podgorski's work shows the same thing at this stage, right? That they're only able to match a large number of predicates. So here's the data we've got, right? I've got 3 path length measures, the data only, the control only, and both, right? And I'm looking at evals. We actually have 4 data sets we gathered these for. We started off with this small mean set. So small refers to the range of values that the search tool has available to it. It's using a fairly narrow range. And we were using the mean of 30 runs to get an aggregate sense for how hard it was. And it turns out that, of course, if it doesn't complete or it fails to terminate, right, the mean is undefined. So we went on and considered the median as well. We also considered a larger range, and that gave us 4 data sets. Rather than just kind of fixating on one of those, since we're sort of trying to support a negative result, right, the paper discusses all 4 of them. And then we have the 3 algorithms, the random one, the genetic algorithm, and the alternating value method. Right? That drops us out with 36 linear models where we're trying to predict how hard it is to get test data as a function of the min, mean, and max path length. We also throw the file into that. Right? The file allows different files to basically have different intercepts in the analysis. So here's the results. First off, for this small mean data set, there's 2 things to notice here. One is that the number of length measures, mean doesn't even show up, is very rare. And in fact, far more interesting is they're all negative. Right? Longer paths are actually leading to less squeeze, which seems very counterintuitive. When we come and look at the large mean set, one of the things to notice is that in this second line here, mean and max have sort of alternate signs. This is fairly common in this kind of analysis when 2 variables are kind of counterbalancing each other. Right? One of the things it suggests is their correlation. This graph is just a visual illustration of that. Statistically, these have really high R-score values, 9.8, 9.9, and so on. And what that means is that you can algebraically basically combine the mean and the max into a single term. In this case, when we do that, the negative term dominates, right? So the only model in this that has a clear, straight-up positive impact, right, is the one that I've highlighted here. And to be honest, the use of min there is a little bit weak because the min pals are not all that interesting in the analysis. In the small median data set, right, we end up with 2 more of these yin-yang pieces, one of which shows a net positive result, and 2 with a net positive result in the large median data. Right? So putting all of that together, out of the 36 models, right, 21 just showed no effect at all. 9 actually showed this negative effect. Right? 4 with a positive and 2 mixed. And the mixed ones I would actually lump in with the negative because the positive side of it showed up with min. Right? So, okay, we're not getting a lot of real strong correlation. Maybe it's a nonlinear correlation. So we tried some nonlinear techniques. The data is sort of somewhat skewed, so maybe a log transformation would help, which is a classic for skewed data. Nah, didn't do anything for it. We tried looking at interactions. We tried a whole bunch of different starting points for the regressions, right? And 1,500 models later, there's just no patterns in this data, right? So in summary, right, we replicated their work with a different set of real-world programs. We actually use static dependencies rather than the original reference experiment's use of dynamic dependencies. And in both cases, right, there's just no relationship showing up between these things, right? So what's next, right? Barzai and Parduski come back with this caution at the end of their paper. They say, look, this requires study. What they're kind of saying here to me is, we're surprised. We don't really believe this. Something strange is going on. And that's a sentiment we would like to echo, right? Something seems odd or off here, but the data is the data, right? One cause for concern in there, for instance, is a recent experiment that involves some squeeziness and failed error propagation, where there seems to be a correlation that contradicts the results we're seeing, right? So that's a piece of interesting future work from my perspective. Thank you very much.